Okay, I'm continuing my endless series of Atwood Machine problems. And so today we're going to do a real pulley. So I have the Atwood Machine has two masses hanging over a pulley, but now I'm going to include a pulley that has mass. So it's frictionless, but with mass. So it's not a real pulley. Okay, so let's just review. I'm keeping a little score sheet here. So the ones I've done so far. The normal basic Atwood machine with two masses, half Atwood machine with the mass on a table, frictionless, inclined half Atwood machine where the table is not flat. This is just a calculation. Half Atwood machine with friction, an inclined half Atwood machine with friction. So I'm really cranking along here. Okay, so the one thing that me said before, there's two things. One is, in these cases, suppose this thing moves down a distance h. Then that one would have to move up a distance h. Because I'm assuming this string does not stretch. So if an unstretchable string, then those two distances have to match in the same amount of time. And that would give these two the same velocity magnitude, which would give them the same acceleration magnitude. So the magnitude of the acceleration for mass 1 would have to be the acceleration magnitude of 2, but in different directions. So if this one's going down, that would have to go up. And that's still true. The other thing that I said was that the tension here would be equal to the tension there because the string is massless, and that's no longer true. Okay, because in this case there is a frictional force on between the rope and the pulley, and that's what's going to make this pulley rotate. But that means that the tension pulling this is not equal to the tension over here, right? Because imagine this is a really heavy cylinder there, and I pull and it doesn't slip. And I pull here really hard, but the thing doesn't move. Well, then this isn't going to move either. So the tension here would just be equal to the weight of this thing. So, but the two tensions would not be equal. Okay, so the tension on the two masses no longer has to be equal because there's a friction interaction between the tension, the rope, and the pulley. So then how do we find the acceleration here? Well, I mean, there's actually two ways to do this problem. I mean, we still have the acceleration the same. And I think what I would like to do is to use work energy. I'm going to use work energy and let this fall a distance h and find the velocity. And then based on the distance and the velocity, I'm going to find the acceleration. And it may be the harder way to do it, but that's the way I think of this right now. And that way I don't have to worry about the tension. Okay, so I'm going to say work is a change in energy. Now I need to pick my system. So my system is going to be M1, M2. Okay, so also I picked some values because I'm going to use these values later. I'm still using 100 grams for this one, 200 grams for that one. The disc, this is a disc, the wheel's a disc, and it has a mass of 50 grams and a radius of 1 centimeter. So I'm going to include the M3 is the disc. Okay, that's in my system. And I'm also going to include the Earth. And so by including the Earth, I have a gravitational potential energy for the system. If I didn't include the Earth, I'd have to do work done by the Earth, the gravitational force. Now, what other forces acting on the system? Well, there is one, right? There is something. There's a tension that pulls on all these objects, but that's part of the system, so I don't need to include that as work done. It's part of the system. There is one force that's exerted on the system, and that's the normal force. So there is actually something pushes up on the pin or holds up this pulley, but it doesn't move, right? The pulley doesn't move up or down, no displacement, so it doesn't do any work. So the total work on the system is 0. So I can say, and I could say up here, there's a couple things. I have the kinetic energy is 1/2 mv squared, and I'm going to say v1 equals 0 meters per second. That's the velocity of that and that. And I can also say omega 1 equals 0 radians per second. That's the angular velocity of that. So kinetic energy for the two masses is 1/2 mv squared. The rotational kinetic energy is 1/2 I omega squared. And I'm dealing with changes in energies, but I'm just writing down the definitions. So I is the moment of inertia of the disk, which depends on how that mass is distributed, and omega is the angular velocity. So for a disk rotated about its axis, I would be 1/2 mr squared. This is m3 because that's disk 3. That's the definition. You can integrate and find that, but let's just take that for granted. Also, if this is rotating and the string is not slipping, then the velocity of the string on the edge has to be related to the angular velocity of the disk, such that v equals omega r. That has to be true because no slipping. Okay. Finally, I have the gravitational potential energy, mgy. So I need to pick where the y value is. It doesn't really matter. And let's put our work energy equation. So work equals 0. And that's going to be the change in kinetic energy. These two have the same velocity. Okay. So please forgive me by saying 1/2, the final 1/2 m1 plus m2 v2 squared minus the initial kinetic energy of 0. So that's my change in kinetic energy for the two masses right here. Now I need the change in kinetic energy for this, so it's going to be 1/2 I omega 2 squared minus 0. That's the definition of rotational kinetic energy. And then I need to do the change in gravitational potential energy. Let me put that down here. So this is going to move down. So its displacement, its delta y, is going to be negative h. So this is going to be minus m1 g h, right? Because that's, I skipped a step. Okay, I probably shouldn't have done. That's the delta. That's my change in gravitational potential energy. Because delta y is negative h. That's okay. Now this one's going to move up. So it's going to have plus m2 gh. That's its change in gravitational potential energy. Okay, so let's clean this up a little bit. I'm going to put in this stuff and this stuff here. I'm going to, omega is v over r right there. So I get 0 equals 1/2 m1 plus m2 v2 squared. That's 0. And then I have plus 1/2 times 1/2, so it's going to be 1/4. And then the mass is going to be m3. And then I have r squared. And then omega 2 squared is going to be v2 squared over r squared. Yes, and those cancel. And then over here I have, I'm going to say plus m2 minus m1 gh. So that's my work energy equation. I want to solve this for v2, the final velocity. So yes, these, let me put it in red. These cancel. And I get the following. Zero equals 1/2 m1 plus m2 v2 squared plus 1/4 m3 v2 squared, right? Because those cancel. And this is nice. You see these all have the same units, and they kind of, you can combine them together. Plus m2 minus m1 gh. And I don't know what h is. I'm just going to go with it. Okay. Now I can factor out a v2 and move that to the other side, and I get negative, subtract from both sides. Well, let's just, I guess it'd be m1 minus m2 now, gh, right? Because it's negative m2 minus parentheses m2 minus m1, so I bring that in and I get m1 minus m2 equals v2 squared times 1/2 m1 plus m2 plus m3 over 4. So now I can divide both sides by this, and I get v2 squared equals m1 minus m2 gh, all of that over 1/2 m1 plus m2 parentheses plus m3 over 4. And that's that. Okay, I can solve for v by taking the square root of both sides, but I'm not going to do that because I know not to do that. But if you did it, it'd be cool. I'm cool with that. Okay, so let's think about this. I want to find the acceleration, right? So here I have my block 1. It starts with v1 equals 0, and it moves down here a distance h, and down here it's going, it's still block 1, v2 equals that stuff. So how do I find the acceleration? Well, the acceleration is defined as a is the change in velocity over the change in time. So I know the change in velocity is just going to be the final velocity, v2. I'm finding the magnitude here. v2 minus 0 over delta t. So I know v2. I don't know delta t. Okay, well, I can also use the definition of average velocity. V average is going to be the final velocity plus the initial plus final velocity over 2. So 0 plus v2 over 2. That's the definition of average velocity if it has a constant acceleration, which it does in this case. And that's also going to be the displacement delta y over delta t, so h over delta t. That's the other definition of average velocity. So I can solve this for delta t. So let's multiply both sides by delta t, and I get delta t equals 2h over v2. Is that right? Yeah. And now I can plug that in over here, and I get a equals v2 over delta t, which is going to be 2h, no wait, delta t, yeah, 2h times v2. Aha! You see, I was thinking ahead. Actually, I just got, been doing a lot of physics problems. So it's going to be v2 squared over 2h. So now all I have to do is put in my expression for v2 right there. And I get a equals, now look at this. I have this whole thing divided by h, so the h is going to cancel, yay. Okay, and then I have to multiply all this stuff by 2. So I'm going to get a equals this stuff. So it's going to be m1, oops, I feel bad now, it's minus m2 g, not the h. Gosh, I'm making a mistake here. I'm just excited. Now I have multiplying this by 2, that's going to be 1/2 times 2 is just going to be 1. So I get m1 plus m2, and then I have plus m3 over 2. And that's it. That's my acceleration. Okay, so now, is there any way we can check this? Number one, can we check the units? Yes, we can. So g has units of acceleration, and then I have mass, and then I have mass. So the mass, the cancel, I get acceleration. That's really good. What about the limit where the mass of the pulley goes to 0? We already did that problem. If m3 goes to 0, then I get that term just goes away. And I can pull out my little handy sheet right here for the acceleration of a pulley with a friction, with a massless pulley, and yeah, I get the same thing. Wait, I have minus m. Oh, I said that was going down. This is cool. That's cool. Okay, so that works. Okay, so now the next step is to do what I do, and that's to put in the values that I picked from before. Where to put my sheet? Here it is. Okay, so I'm going to use these values, and let's put them in and calculate this thing. Okay, there you can see the thing. Okay, so m1 is 0.1. I didn't have to do that. 0.05 minus, I could have done that. Okay, 9.8 times, so that's that whole top term. Now on the bottom I have m1 plus m2, which is 0.15. And then I have m3 is, I picked that as 0.5, enter, 2 divided by, plus, divided by. And I get 1.225 meters per second squared. I'm pretty happy with that. You do notice the mass of the disk matters, but the radius did not. The radius didn't matter, it canceled. Also, there's another thing we could check. What if I increase the mass of this to some ginormous value? Okay, it's 5,000 kilograms. So if I put 5,000 kilograms down here, then the acceleration is going to be very, very close to zero. That makes sense. Okay. Now, so the other problem, let me just give you a preview here. What we're going to do is actually have a tension. Let's say this is a heavier thing. Tension T1 pulling down and T2 pulling down that way. T1 is going to have to be greater, and so that's going to make the whole thing rotate this way. But that's the same tension pulling up, and this is the same tension pulling up. So we essentially get two tensions here. We have to solve for two tensions, and so it makes it a little bit more complicated. And then we have to deal with the torque and the change in angular momentum of the disk. And I think we should get the same answer. But in my mind, the work energy method just seemed like it'd make more sense, so that's why I did it that way. Okay, that one wore me out. I'll probably do the next version on another day, but working along here.